Hello, and welcome to this video. We're going to discuss conversions between decimal numbers and octal numbers, and decimal numbers and hexadecimal numbers. But before we look at the actual process there, we want to define the term algorithm. An algorithm is a term that's widely used in mathematics and computer science because it provides a basis for a lot of what we're going to do. So whether you're doing simple multiplication or complicated calculus problem, you follow a predetermined set of rules or steps, which we're going to call an algorithm. And to kind of more clearly define that, we're looking at a process or set of rules to be followed in calculations or other problem-solving operations. It has a finite number of steps, and these steps, though, may at times involve repetition. So it might be that you get to step 4, which says, if something happens, repeat steps 2, 3, and 4. And you end up going through a process multiple times before you get to the end of that process. And algorithms are something that are very widely used by computers. We look at some real-world examples of algorithms. The process of going through and tying your shoe. It's a process or set of rules. We're solving a problem where we want our shoe to stay on tightly. And it's something that you're going to repeat and go through regularly. Writing an email is another process that you're going to go through. You open or log into your email, determine who you're going to write the email to, a subject, compose the email, hit send. Or having a conversation via text message where you read a message, respond, hit send, the person reads the message, they write a reply, they hit send, and so you see that repetition of steps as you go through that algorithm. When we look at number systems, and we looked at in the last video how to convert to the binary number systems, the problem that we had converting from binary to decimal is that those numbers get very big or have many digits very quickly. So there are some other number systems that are used that we're going to be able to use less digits and easily convert back and forth between different cases, different situations. So if we take a look and review real quick, we have the decimal number system that we talked about. Remember, possible digits, bases, the base is 10, the possible digits 0 through 9. My binary number system, the base is 2, the possible digits are 0 and 1. And we look at the octal number system, obviously it's going to be base 8. Okay, and my possible digits are going to be 0 through 7. Remember that the possible digits is always one less than what my base is. And it's important as we go through this that you think about how numbers are created, and that for all of my number systems, each digit represents a different weight. The least significant is going to be my farthest right, and most significant is going to be farthest left. So if we review real quick, converting and how decimal numbers are created, if I take a number 357, my farthest right is my least significant, and that was 7 times 1. Whereas the 3 represented 3 times 100, because it was the most significant. That was 3 hundredths, which is very significant in my overall number. And we look at it with binary numbers, it's a little bit harder because you only have those two options. But this red one is my most significant bit, and it was multiplied by 2 to the third, which was 8. So remember, we took our base, raised it to an exponent. And we're going to follow that same process today, that same algorithm that we used to convert between binary and decimal, which was called weighted multiplication, to convert between decimal and octal. So if we take an octal number, and I know and I can check that this is octal because it's got the little subscript here that tells me it's base 8, and then it has 3 digits, and all 3 of those digits are legal digits. They're 0 through 7. Okay. My least significant digit is going to be the 3, which is at my exponent, where my exponent is 0. My most significant digit is going to be the 2, where the exponent is going to be 2. And my base in this case is 8. So I determined what my least significant exponent was, and then going right to left increased. My most significant exponent was a 2. So we're going through it, and then the next thing that I need to do as I'm going through that is then multiply and add. So that same process, I put in my exponents here. This is 8 to the 0 power, 8 to the 1, 8 squared. So we go through and now we're going to multiply these two numbers together, these two numbers together, these two numbers together, and then add up their total. So I get 2 times 8 squared plus 5 times 8 to the first plus 3 times 8 to the 0. I like to start from this side because I always know that anything to the 0 power is 1. So this is 3 times 1. And then it's easier to do my multiplication. So then I just take 5 times 8 because I know 1 times 8. And then next time through, 8 times 8 is 64. I multiply that by 2. Then I get 128 plus 40 plus 3 to give me my overall number and result there of 171. And it's important as you're going through these problems that you always label what your base is. So that I can say 253 in octal equals 171 in decimal. Otherwise it can be very confusing. You don't know what base you're working in as you go through that. So we'll take a look at 2 more examples, slightly larger numbers this time, but the same process. My least significant digit is going to be that 0, which is going to be at 8 to the 0. My most significant digit is going to be the 1. This was at 0, this one's at 1, this one's at 2, this one's at 3. So that'll be 8 to the 3rd, and my base is 8. So I end up with 1 times 8 to the 3rd plus 6 times 8 squared plus 5 times 8 to the 1st plus 0 times 8 to the 0 power. This becomes 0 times 1 plus 5 times 8 plus 6 times 64. And then I have to figure out what is 64 times 8. That's how I get my 8 cubed. This becomes 1 times 512. So I get 512 plus 6 times 64, which is 384, plus 5 times 8, which is 40, plus 0 times 1. So overall, I get 936 in base 10 is my value. Oops. So I can go back up here to the top and say that this equals 936 base 10. Go through this example. Again, it's the same size. So it's a little bit easier. I know that this is 3 times 8 cubed, which will be 3 times 512, plus 2 times 8 squared, so 2 times 64, plus 5 times 8 to the 1st, 5 times 8, plus 7 times 8 to the 0 power, 7 times 1. So 3 times 512, I get 1,536. 2 times 64 is 128. 5 times 8 I know is 40. And 7 times 1 is 7. So overall I get 1,711 base 10. That's my answer. One way to kind of spot check that these numbers are correct and that you're at least on the right track as you're going through this conversion is notice that the number that is in the bigger base, so in this case my bigger base would be 10, that this number, my answer, should look smaller than this number in a smaller base. Because I can group together more 10s needing less digits here than when I have only 8s to group together. It's going to take me a little bit longer. If you think back to my binary conversions, it applies that same way. And just like I can apply the algorithm of weighted multiplication to go through and convert, I can also go through and apply the algorithm of successive division to convert back from a decimal number to an octal number. So if I go through and look at our example from before, I want to kind of check my answer here. The value was 171. So I'm going to take my original number in decimal format. I'm going to divide it by my new base that I'm converting it into. And this gets a little bit more difficult. You're going to have to look at and determine remainders. So if we take a look at this, I start with 171, and I'm going to divide that by 8. You notice I'm writing this kind of backwards. Normally you would say 171, and you would divide it by 8 this way. But we don't know how many times we're going to need to divide. So one process or way of doing it is to kind of write it down as we're going through our division, and you'll kind of see how that works. So if I think about it, how many times does 8 go into 171? Well, 8 goes into 17 2 times, then which would give me 16, which would leave me 11 left over, so it's going to be 21. If you think about it, 8 times 21 gives me 168. So if I do 171 minus 168, I'm going to get back a remainder of 3. And remember that remainders are the pieces of my answer. So when I'm looking at my answer up here in base 8, this 3 becomes my least significant bit part of my answer. And then this number, 21, how many I was able to pull out, becomes the new number that I'm going to divide by my base. So 8 goes into 21. Well, we know that the closest we can get is 16. So 2 times 8 would give me 16. 21 minus 16 gives me a remainder of 5. Becomes the next part of my solution. I bring the number that I multiplied by down here. 8 goes into 2 0 times. Because I can't get anything out of there, well, how many things do I have left over? I have 2 things left over. So my answer is 253 in base 8. If you look back in your notes, that's what we had a few slides ago. This is obviously going to be a little bit more challenging than converting from base 8 into base 10. And it's something that you're going to need to practice with. You will probably use your calculator or want to use your calculator. Unfortunately, you are not allowed to use a calculator on the AP exam. So you do have to think about and do some math as we're going through this. We'll take a look at another example. I'm going to take my 78 and divide it by 8. Well, I know that 9 times 8 gives me 72. 78 minus 72 gives me a remainder of 6. So remember, that becomes my least significant bit there. And then the 9 drops down. How many times does 8 go into 9? Well, I can do 1 times 8 gives me 8. 9 minus 8 gives me a remainder of 1. And then I have 1 thing left over to divide. 8 goes into 1 0 times. So when I do, I have a remainder of 1. And again, my answer looks somewhat correct. Smaller base is octal, bigger base is decimal. This number looks bigger than this number because this base is smaller. And if I go through the last example, 405, 8 goes into 40 5 times. And it goes in, then I would have 5 left over. That's as many as I'm going to get. 50 times 8 gives me 400. So 405 minus 400 gives me a remainder of 5. Take my 50. I'm going to drop that down. 8 goes into 50. I know that 6 times 8 is going to give me 48. 50 minus 48 gives me a remainder of 2. I take my 6, I drop that down. 8 can't go into 6, so I'm going to have 0 left over. Oops. And as I go through this, then I do 6 minus 0 gives me a remainder of 6. And again, that number looks slightly larger than the number in the higher base. So that's how we can take those two algorithms and apply them to solve different problems, but we're going through the same general procedure. And we're going to do that one more time with our last base, which is hexadecimal. So if we think back to this slide from before, we went through decimal, binary, and octal. And we have one more base that's very important for us to go through. So hexadecimal is going to be base 16. If you think about base 16, though, we only have numbers 0 through 9. So to represent those extra values in our base 16, we use the first 6 letters of the alphabet. So when I want to represent 10, I use the letter A. I want to represent 11, I use the letter B. When I want to represent 12, I use the letter C. 13, I use the letter D. 14, I use the letter E. And 15, I use the letter F. And the reason being that if I used 1 and 0, those are digits, and I would think that my number was much larger. And we're going to use that same process that we've been using, where we can break a number down and multiply it by the weight of its position to get my different values when I look at hexadecimal numbers. So if we take an example, 2A7, so notice that we have a letter here, and we have to make sure that we convert that correctly as we go through it. Many times I will go through and I will actually kind of write those values over on the side of my paper, so I remember that I'm going to go 0 through 9. The next value would be 10, and that's where I start with my alphabet. Then I have 11, 12, 13, 14, and 15 to finish out my bases. So my least significant digit here is always going to be at 0. Then I have a value at 16 to the first, and then 16 to the squared. So my most significant digit there is 2. My base is 16. I'm going to go through my values with that same process, that same algorithm that I've been using. So this, remember, starts at 16, or my base to the 0 power, my base to the first power, my base to the second power, my base squared. So this becomes 7 times 16 to the 0 plus A, remember, is 10. So 10 times 16 to the first plus 2 times 16 squared. So this becomes 7 times 1, which is always the value that I have there when a value is raised to the 0 power, plus 10 times 16 plus 16 squared, which is 256, times 2. So I get 512 plus 160 plus 7 to give me a value of 679 in base 10. So I can say that 2A7 base 16 equals 679 base 10. And we'll repeat that process, get a little bit more practice. this is going to be my 16 to the 0, 16 to the first, 16 squared. So my least significant digit, most significant digit, my exponents there, base is 16. So I get 3 times 16 squared plus c times 16 to the first. When I think back to my notes, c, remember, is 12. And then I have f times 16 to the 0. Well, f is 15. So I have 3 times 256 plus 12 times 16 plus 15 times 1. Might be a little bit easier to see exactly what's going on if I put these in parentheses. So you look at your order of operations. So I get 768 plus 192 plus 15 gives me a final value of 975 base 10. Here I'm going to have to go one extra exponent. So I get 1 times 16 cubed plus d times 16 squared plus b times 16 to the first plus 0 times 16 to the 0 power. So if I think about, I'm going to now multiply 256 times 16 again. So I get 1 times 4096 plus d, which when we go through an our conversion is 13. B is 11. So we get 13 times 256 plus 11 times 16. So you can already tell this is going to be a pretty large number, and 0 times 1. So I have the 4096 plus 3328 plus 176 plus 0, a total value, or final value, of 7,600. And again, you can look at this number looks much bit larger than this number. Even though they're both 4 digits, this one has a 7 in what we think of as the most significant digit. This one has a 1 in that most significant digit area. So normally people would say this is a larger value. Now where it gets difficult with hexadecimal is our successive division. You're going to be dividing by 16, which is something that's definitely not going to be comfortable for a lot of people. And it's something that you just have to be very careful with. So if we take just a simple number, like 171, our example from before, and divide it by 16, think of 16 is going to go into 17 one time, and that would leave me with 11. Well, 16 can't go into 11, so it's going to go 10 times 16 gives me 160. 171 minus 160 gives me a remainder of 11. And something you should always keep in mind is that this remainder can never be larger than or equal to my base. So if for some reason you got a remainder of like 21, you should immediately realize that's going to be too large and something went wrong. You need to multiply your value one additional time. Again, remember, we don't want to put 11 in my answer because that's going to add an extra digit. If I put a 1 and a 1, that represents 2 digits. So I have to convert that 11 into its letter equivalent, which is a B. Then I take the 10 and put my 10 down here. 16 goes into 10 0 times. Think of it this way, if you have $10 and you are trying to buy something that costs $16, can you buy it? No. So I can get 0 of those things, so then I have 10 minus 0, so I still have the $10 that I started out with. 10 is the letter A. So 171 in base 10 equals AB in base 16, or in hexadecimals. 2 more quick examples, just to see that process, that algorithm run through again. I take my 168 divided by 16. I know that 16 times 10 is 160. So if I take 168 minus 160, I get a remainder of 8. And sometimes you will see hexadecimal represented with an H instead of the value 16 as its subscript. Both of them are acceptable. It's kind of a point of preference. Then I take my 10. I'm going to put that down here. Again, 16 goes into 10. I know that it can go in 0 times. So I end up with a remainder of 10, which I have to convert into a letter. To get my value. Here's one that looks like it's going to be much more difficult. Sorry about that, very hard to read. There we go. But if I look at it, 16 I know goes into 32 twice, and then there's no way that 16 can go into 5, so this becomes much easier than I actually think it might be. 200 times 16 gives me 3,200. If I have 3,205 minus 3,200, I'm going to get a remainder of 5. I take my 200 and drop it down. Now here I have to think of how many times is 16 going to go into 200. Well, I know 16 times 10 is 160, and I figure out I can add in 2 additional 16s, groupings of 16. It gives me 192. So 200 minus 192 gives me a remainder of 8. I take my 12. 16 can go into 12 0 times. So I know that I have 12 minus 0 gives me a remainder of 12, which I have to convert into the letter C. And I get C85 in base 16 as my answer. Something to think about as I'm going through this is that twice I went through and I had 171 in base 10, and I converted it into base 16, and I converted it into base 8. So all of those I can then say are equivalent. As I've gone through, I've done the same conversion as I was going through it. In base 8, my answer was 253. And then when I was in base 16, my answer was AB. So again, as you look at the bases, the largest looking number is in my smallest base, and the smallest looking number, this one only has 2 digits, is in my largest base. You could extend this and go through and determine what this is in binary, but we're going to actually leave that for the next presentation. So we'll show you a little shortcut for doing that conversion. So we've got one last slide. Take a look at that process of counting. And it's going to be important, and this will lead us into our next video of how counting can make our lives a little bit easier in this whole conversion process. But if I were to take a bunch of decimal numbers and just count from 0 to 20, and I go through in binary and we looked at how my bits flip every other bit because there's only 2 options, and have those go through. With Octal, I have a lot more bits to go through, so once I get to 7, I have to reset this least significant bit to 0, which means that I carry the 1, and now I have 1s in my most significant bit till I get to 7 again. The next value, I reset that again to 0, and I add to my most significant bit. And looking at hexadecimal, I have to get all the way to 15 to reach the end of my possible digits, to get all the way to F. And then when I get to 16, that F resets to 0, and I carry the 1. So you could, at any point in this table, go ahead through and write equal signs as long as you have these numbers clearly labeled with their bases. So this value in binary is equal to this value in octal, is equal to this value in decimal, is equal to this value in hexadecimal. All right, you're going to go through some practice. Good luck.